Now that we've seen the definition of a limit, we're going to use it to prove the sum limit law, which, as a reminder, says that if f and g are two functions that both have a limit as x approaches a, then the limit as x approaches a of f plus g is equal to the sum of the individual limits. Since we're going to use the definition of a limit, you may want to refresh it, but we'll see it as this unfolds. Not exactly, but we're going to be using it. But before we get started, we're going to do an aside. I don't know if it's legal to do an aside before you even get started, but I'm going to do it. There is something called the triangle inequality. And it says that for real numbers a and b, the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. To show why this is true, I'm just going to make a few statements here. A is less than or equal to its own absolute value. And it's greater than or equal to the negative of its own absolute value. And we can say the same thing for b. And we can add the two compound inequalities together. If I factor out the negative on the left-hand side, then I have negative of absolute value of a plus the absolute value of b is less than or equal to a plus b, which is less than or equal to the absolute value of a plus the absolute value of b. This leads us to the statement that the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. How, you may ask? Suppose you were solving an absolute value inequality, say absolute value of x is less than or equal to 4. You might have been taught we're going to split this up into two inequalities. One of them is going to say x is less than or equal to 4. The other is going to say that x is greater than or equal to negative 4. But if you look at what we have, that really puts x between negative 4 and 4, doesn't it? In fact, this may be how you were taught to solve absolute value inequalities when the absolute value was less than a number. My point here is that if the absolute value of x is less than or equal to 4, then x is between negative 4 and 4. Folks, what we just did here in the last step from 3 to the so was we went backwards here. Negative absolute value of a plus b is playing the role of negative 4. Absolute value of a plus absolute value of b is playing the role of 4. And the result, absolute value of a plus absolute value of b is playing the role of 4. Okay, now we're going to set that aside. I apologize for that one. Okay, back to our limit statement. We're going to prove this now. We're going to start by labeling each limit. So let the limit as x approaches a of f of x equal L. Then, now I'm going to use mathematical shorthand. For every epsilon greater than 0, there exists a delta. And since this is associated with f, and we also have a g running around, I'm going to use delta 1. There exists a delta 1 greater than 0, such that if x minus a in absolute value is positive and less than delta 1, then the absolute value of f of x minus L is less than, I'm actually going to use an epsilon over 2. I guess I should call that epsilon over 2 there as well. The reason for that will be evident in just a few minutes here. I've dealt with f. I'm going to write the same thing for g. I've written down basically the same statement, except for the limit as x approaches a of g of x, we have an m. And in that inequality, we have an m. And instead of a delta 1, I have a delta 2 to associate with g. Now we're going to do something that's a little bit tedious. I'm just going to box that over there. We're going to let delta be the minimum of delta 1 and delta 2. Then if the absolute value of x minus a is less than delta, we have the absolute value of x minus a less than delta 1, and the absolute value of x minus a less than delta 2. All we're really saying there is if I pick the smaller of delta 1 and delta 2, then I'm going to satisfy the premise of each inequality statement for both f and g. Since that's the case, we have that absolute value of f of x minus L is less than epsilon over 2, and the absolute value of g of x minus m is less than epsilon over 2. You may say, we already said that. Yeah, we kind of already did say that, but there's a nuanced difference here. What we're doing here is we've applied the limit definition to f, and then we applied the limit definition to g. But now we want to sew it up, and now we're making a statement that says if x minus a in absolute value is less than delta, then we've got these two inequality statements, one with f and L and one with g and m, and it's a way to kind of cover all our bases, dot our I's and cross our T's. Now we were after a sum, right? We're proving the sum limit law, so I want to be able to add things together. And so I'm going to add absolute value of f of x minus L plus the absolute value of g of x minus m, and that is less than epsilon over 2 for f of x minus L absolute value plus epsilon over 2 for g of x minus m in absolute value. And that happens to equal epsilon. Now, the statement that have been building toward is if x minus a is positive and less than delta, or the absolute value of x minus a, then I now have this conclusion that the absolute value of f of x minus L plus the absolute value of g of x minus m is less than epsilon. You see, I'm trying to make a statement that looks like the definition of a limit. Now I'm going to move this over, and we're going to use the triangle inequality. Remember, the triangle inequality said that if I have the sum of two absolute values, then that's greater than or equal to a single absolute value with the sum inside. And so absolute value of f of x minus L plus g of x minus m is less than or equal to epsilon. Oh, cool. So if I rearrange what's inside the absolute value, then I have the absolute value of f of x plus g of x minus the quantity of L plus m. I just went ahead and factored out the negative and combined them together. And absolute value is less than epsilon. This, by the way, the adding of the two epsilons is why we used epsilon over 2. So at this point, we have simply an epsilon. Now, if x minus a in absolute value is less than delta, then the absolute value of f plus g minus L plus m is less than epsilon. And that exactly fits the definition of a limit. So the limit as x approaches a of f of x plus g of x is equal to L plus m. But remember, L was the limit as x approaches a of f of x, and m was the limit as x approaches a of g of x, and now we have the limit of the sum is equal to the sum of the limits, which is what we wanted to prove.